So today we're going to take our linear functions and apply them to the real world. In basically this video, I am going to walk through three different problems. They're going to match up with our case 1, case 2, and case 3 examples that I've talked a little bit about in the past. So the whole video, let's apply these linear functions to real world situations. So we're going to start off with a case 1 example. This is going to be an example where you know the slope, rate of change, and you know the y-intercept, the initial value, and it's really easy to write the y equals mx plus b equation, the slope-intercept equation. We've already done a couple of these in the past. There was the one with the hot air balloon in Jacksonville, Florida. This is just another example. So imagine that Julia has already read 40 pages of her book, and she reads at about 1.5 pages per minute. We're going to write an equation to model the pages that Julia has read. So I've already talked to you about the fact that it's really easy to find your slope. So I want you to look at this equation. I'm going out of order here for a reason. And I'm actually asking you to find the slope in the words here. So did you find it that it's the 1.5 pages per minute? And the reason we know that is we can see the two units, the y unit and the x unit, pages per minute. Slope has two units, one for the y's, one for the x's. The reason I asked you to jump down here and kind of start with that is that helps you kind of define your variables. If the slopes are in there, it's really easy to know who is your dependent and who's your independent. Remember, pages per minute. That pages would be on the top, minutes would be on the bottom. So pages would go with your y and minutes would go with your x. So it's kind of easy if you have the slope to be able to define your variables using those units off the slope. Also, if time is involved, minutes, days, seconds, years, more than often than not, it is your independent variable. It would be your x. There are exceptions to that rule, but just for the most part, that happens. Again, I mentioned in class, you hear that phrase, something happening over time. That puts time in the bottom. That puts time as your x in the slope formula. All right, so having said that, what is this 40? Well, that would be your y-intercept. That's your initial value. She started 40 pages in her book. So at time 0, at 0 minutes, she has 40 pages already read. So now it's really easy to write your slope-intercept equation. So go ahead and do that. Y equals mx plus b. Slope goes in front of the independent variable, and the y-intercept is the constant or the caboose, y equals mx plus b. So now we could graph that. So I'm going to encourage you to get a piece of regular graph paper here, make a y and an x-axis. We don't need quadrants 2, 3, and 4 because in this case, we're not going to have negative minutes and we're not going to have negative pages. So this graph is only going to take up the first quadrant. And what I'd like you to do is make a graph of Julia's reading. And I'll come back in a second and talk you through it, but do this, take it seriously, guys, so that you can get used to making these graphs. Okay, so the first thing your graph is going to need is, did you put a title and did you put labels? We've talked about that in the past. Your labels are really easy because they're the definition of your variables, and the title needs to describe what's going on in the graph, okay? So you should have put minutes down here and pages read up here, okay? And a title, Julia's reading or something like that. Now, once you do that, you need to set the scale. So you have to think about reasonable scales, and you have to make sure that they stay the same. Now, your scales might not match mine as I flip to the answer here, or my answer, I should say, but they do have to go up by the same amount in the x direction. You don't jump from 1 to 2 and then have the next thing be 7. They all have to have an equal amount per interval. And it doesn't have to be the same interval on the y, but it does have to be equal going up. So let's see my graph. Okay, so I started with a break in the graph so that you want your graph to be centered. So you don't want the line to be way up here. So if there is sort of a high starting point, you can do a break in the graph. I am going by 5 pages. And 40 would be my y-intercept. I'm going by minutes out here, so you see 1, 2, 3, 4 by ones. Now, it is really hard in my scale to go up 1.5 and over 1. So using the slope to do the graph is impossible. I just need another point. So I chose to pick a number, and I picked 10 because that is easy math. And I plug it in. I substitute it in for x, and 1.5 times 10 would give me 15. Add it to 40 would be 55, and there's the second point. And I can put in my, in this case, array, because you should have an endpoint here. You're not going to go into the negatives, but she could keep reading. Again, this isn't going to go on forever because the book will end. So this will be linear as long as she's reading at that same rate until the book ends. So there's a good graph. Don't forget title, labels, and hopefully you understand kind of those good graphing techniques. All right, let's go on to case 2. This case, you know the slope, the rate of change, but the point is not the initial value. Okay, so we don't have the y-intercept here. So let's read this problem. You've been draining your hot tub for 40 minutes. So you pull out the plug, basically. It starts draining and you walk away. After 40 minutes, you go back and your current level is that there are 600 gallons still left in the tub. Now the tub drains at a constant rate, which is 10 gallons per minute. We're going to write an equation to model the volume of the tub over time. So again, I can hear a slope in there. Do you hear it? What is the slope in this situation? And did you say that it was losing 10 gallons per minute? Again, don't forget the negative. It's going down. It's draining. So the reason I go there first is the top. The gallons will be your y unit and the minute will be your x. So defining variables becomes really easy when we have a slope, a rate of change in the problem. Okay. So now the question is, what is this 40 minutes and 600 gallons? Is 600 the b? Can we just say y equals negative 10x plus 600? And the answer is no. So what we need to do is write a point from this other information. What is that point? Remember that x is minutes, so 40 minutes. Gallons is your y, so 600, there is your point. This is not the y-intercept, so we cannot go right into y equals mx plus b. We have to use the point slope form. All right, so now put this information into the point slope form. Let's see how you did. Don't forget y minus the y coordinate equals the slope times x minus the x coordinate. But this is not useful. Remember, there are an infinite number of point slope forms for any equation, so we never leave it there. It's a great place to start, horrible place to end. So we are going to transform this into slope-intercept. And can you now do that? Right, so you should have done distributive property. And once you've done the distributive property, watch your sign, a negative times a negative is a positive. And now I want this guy to move over. Now remember, opposite sides, opposite operations. So you're going to add 600 to both sides. Now, if your brain does a subtraction, write down plus 600 on both sides. But if you can do that in your head and get right to here, you are good with me. So this is the equation for the hot tub. Oops, I wanted to ask another question. I thought it was on the next page. So before we move on, what is this 1,000? So that 1,000 is how many gallons there was in the hot tub when you started. It was the initial amount of water in gallons. So there were 1,000 gallons before you pulled the plug. All right, let's go on to our last case, 3. So a candle is 6 inches after burning for an hour, and after 3 hours, it is 5.5 inches tall. Model the height of the burning candle with an equation. 6 inches, 1 hour. 3 hours, 5.5 inches. All of those numbers have 1 unit. There's no inches per hour, nothing like that happening here. So you're missing the slope. So in this particular case, we do need to start by defining our variables. We don't have that slope to help us. So the question is, who is our x and who is our y? We've got inches and hour. So is it inches per hour or hours per inch? Does the time change based on how tall the candle is? Or does the candle change depending on how much time went by? I mean, that's a silly question. But again, looking at that time, that's going to shout to us that that would be the x. And that would make the y. And don't forget, when we define variables, we need to have those units in our definition. So now, can you write the 2 points? So get these two into coordinate points. So one of the points should be the 1, 6. And now be careful, because they're kind of in a different order here. The other one should be 3 and 5.5. Okay, so now we need to write an equation. So, we need to find the rate of change. So right now your job is to find the slope of these 2 points. So here is the slope. Let's see how you did. So I chose to go 5.5 minus 6. Doesn't matter, which order, but once you pick that order, you have to do these in the same, right? Same order. So it was dropping 0.5 for every 2. I'm going to divide that out to make it a unit rate. And the candle is dropping by 1/4 of an inch an hour, 0.25 inches going down every hour. So now I have the slope, and I actually have a choice of points. So now can you write a point slope form for this equation? Now you have a choice of 2. And obviously I'm going to pick one or the other. And I chose the first point, avoiding the decimal, I guess, here. But y minus the y coordinate equals slope times x minus the x coordinate. Horrible place to leave this equation, as we've talked about. So transform that, please, into slope-intercept form. So we should have done the distributive property, again, watching your signs. And at this point, you're going to add 6. And when you add 6, and I'm just showing you that because some people, they see this equation and they just want to subtract a 6. Like, you have to do opposite operations. So, if your eyes are fooling you, you guys all know what to do. But if you're sort of just going over there and slapping a minus 6, write the step like we did in Unit 2. I don't grade the step at this point in time, but if you need it, write it. And there would be our slope-intercept form. Okay, so let's talk about this guy a little bit further. So I had that covered up, but there he is, okay? All right, what is the slope? What does this minus 0.25 mean in terms of the candle? So what that is the rate of change. It's telling you how the candle is going down. So this is kind of one of those wider candles, if you know what I mean. It's not like a birthday candle because it's dropping 1/4 of an inch per hour. So it's just telling you how that candle height is changing, and then it's going down 1/4 of an inch per hour. What does this y-intercept represent? What is the 6.25? And did you say that is the initial height of the candle? So when you bought the candle, it was 6 1/4 inches, 6.25 inches tall. So you get that information off of that equation. All right, let's take it just one step further here to finish up today. Let's stick with the burning candle. Use the equation that we have up above to figure out what the height of the candle is after it has been burning for 8 hours. So how do we do that problem? Remember that x, your definitions really matter here. X is the number of hours. So we're going to substitute the 8 in for the x, and we're basically going to do the math. So negative 0.25 times 8, and then add the 6.25, and we get 4.25. And what that means is after 8 hours, the candle will be 4.25 inches tall. Pretty cool. Last question of the day. Use that equation to determine how long it'll take for the candle to completely burn to nothing. Now what do you do with this one? Remember your definitions. X is hours, Y is the height in inches, and we want it to be nothing. So this time we're going to substitute 0 in for the y, and you've got a two-step equation to solve back in Unit 2. Now again, I'm not grading on steps, but it is absolutely okay to write them. You should have started by subtracting 6.25 on each side, and then we're going to divide by the negative 0.25, and our x will be 25. What does that mean? It means that in 25 hours, that candle is gone. So if you lit it, it would take just over a day to completely burn down. So what I've done today is giving you 3 different examples of real world problems. It's actually really, don't get all flustered about words, guys. You're all great mathematicians. Sometimes connecting the words scares mathematicians, but it's really some easy ways to see things inside these problems. And I hope these 3 problems have helped you feel a little bit confident about when reading a word problem for a linear function, what to kind of look for as you start to write that equation and then use the equation to answer questions about the situation. So now it's your turn to practice. And like I said, when I see you next, we'll talk these through a little bit more. And then we're going to be heading into parallel and perpendicular land. Guys, I hope you have a great day.